Hi, welcome to Statistics Online. I'm Naomi Lowe, and this will be Lecture 1, Part 2. For Part 2 of Lecture 1, we will cover number 3, 4, and 5 on the outline. First, I'll give you some examples of graphs, ways that we summarize data into meaningful pictures. And then we will learn how to make a frequency table and how to make a histogram. We will look at different types of histograms and then move on to distributions or shapes of histograms. And after that, we will look at some ways that graphs can be misleading so that you can keep your eye out for these little tricks and understand the information yourself. All right. Now, when we're summarizing data using graphs, what type of statistics are we using? Remember from Part 1, descriptive or inferential? Descriptive's correct. We're using descriptive statistics if we're creating graphs and summarizing the data that we actually have collected. Now, that doesn't mean descriptive and inferential statistics are mutually exclusive. Many times we run inferential stats. We're asking a question about a larger population with a small subset of sample data, but we still use descriptive statistics to create graphs and summarize and look at the data that we do have. So many times you're going to use both descriptive and inferential statistics. Let's take a look at our first graph here. This is a pie chart. This pie chart gives you percentages, counts. You can see here 33% C, D, 10%. What type of variable do you think you would use a pie chart for? Remember back to our variables. If you guessed nominal, you're correct. A pie chart is great for categories, for nominal variables. We could take your political party that you belong to. I could ask you that and summarize it in a pie chart. Say 33% of you are Democrats, 29 Republican, and so forth. You could use it on hair color, and any nominal variable, a pie chart works great. Pretty self-explanatory, easy to create. The next graph we are going to look at is a bar graph. On this side is a bar graph. And a bar graph is similar to a pie chart. It's used for categorical variables. You take the categories and then you just list here on the y-axis the frequency, and you create a bar that shows you the frequencies for each category. These categories could represent any nominal variable. This could be, it says brain region, but it could be hair color. We could have blonde, and that would be the frequency of blondes in the class. Number 2 could be brunette, and it would show that we have mostly brunettes in the class. And redhead down here. And then 4 is a little hard to see, but it gives you the frequencies of a nominal variable. This says brain region, so these are 4 different brain regions. It could be the amygdala that's involved in emotion, my favorite part of the brain, and it's taking the frequency of receptor binding. So here, this receptor, that certain neurotransmitter, binds about that much in the amygdala. And then let's say that this is the hypothalamus, another part of the brain. It looks like that receptor binds a lot there, and in these other parts of the brain, not quite as much. So it gives you some meaningful information. Now this graph over here is similar to a bar chart, but this is what we call a histogram. And a histogram, can you notice the difference between the histogram and the bar chart, at least in appearance? The difference in appearance is that the bars, these bins, touch each other. The bins touch each other because it's meaningful. They have meaningful connections. A histogram is not used for a nominal variable. A histogram is used for continuous variables. So something like height. You could take height in inches, and instead of creating a bin like we do for every single number, because you might have someone who's 5 feet 5 inches, 5 feet 6 inches, 5 feet 6, and a half inches, and so you're going to have a lot of bins if you do it that way. Instead of doing that, we group the bins, and so you might have 5 to 6 feet in one bin, 6 to or 5 feet 2 inches to 5 feet 4 inches, and so on, and it gets taller as you go this direction. So a histogram on the x-axis has whatever variable you're looking at. It could be height, it could be IQ, but it's typically a numeric continuous variable. And they touch because where one bin ends, the next one begins. And over here is just the frequency of people who fell into each of these numeric bins. Another type of graph, kind of a cross between a graph and a table, is the stem and leaf diagram. And I do not believe this one is in your book, so take a close look. The stem and leaf diagram is sort of like a histogram, except it has the actual numbers included in there. Let's say that these were the ages of a class. Okay? What you do is you list the tens digits here. So this would be 10, and then the units digits here. So this means that there was one person in the class who was 19 years old. And then there was someone who was 22. There was another person who was 25, another one who was 26, 27, 28, and 29. So there was only one person who was under 20 in this class. In their 20s, there was 1, 2, 3, 4, 5, 6 people. So it gives you a visual of ages. It kind of summarizes it both visually, but not only do you know that there were several people in their 40s, you know exactly that the age of each of those people in their 40s, 42, 3, 4, and so on. You know there were 2 people who were 48 in the class. So it gives you a nice visual, and you'll see if you turn it this direction, it kind of looks like a histogram. I'll pull my histogram back up here. And if you compare these two, you can see the histogram shows you that most people here were around 65 inches tall. And this shows most people, so it gives you an idea of where most of your data falls. Most of your people are around 40 something here. But here you don't know, if they were exactly 65 or just a little bit over or just a little bit under. Here it tells you the exact measurement, so it just gives you a little bit more detail. All right, so we've taken a look at some of these graphs. We'll come back to them later when we make a histogram. Now I want to show you how to make a frequency table. Here are the steps for making a frequency table. First, you need to list the possible values. These are any values that can be taken. And then second, you need to count the scores. So you actually collect data and then you count each of these values, how many people scored. Let's say we're doing a test of stress rating. Okay, we're going to use some numbers. They asked a stats class the very first week of class how stressed out they were. 0 meant I'm not stressed at all, this is a piece of cake. And 10 meant I'm totally stressed, I can't handle it, life is going to end. Maximum stress is 10. So they asked them, how stressed are you from 0 to 10? And they rated either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of our possible scores are 0 through 10. Then you need to count how many people marked 0. How many people marked 1, how many 2, 3, and so on. You count the scores, make little tallies for them. Third, you are going to count up those tallies to get a frequency. So if you mark 10 people, mark 0, then you just tally it and write a little number 10. Now you have a frequency. That's pretty much what a frequency table is. And then in addition to this, we are going to get the percentage of each of those scores or the frequency. Because, if I tell you, 10 people marked 0 in the class. What if we have 1,000 students in the class? It doesn't tell you a whole lot. The percentages tell you a little bit more information. You just take the frequency, divide by the total number of observations, in this case the total scores from students, multiply by 100 to get the percentage. So let's try one. If you don't have your book open, you can follow along on this example, page 7 of your Aaron and Aaron textbook. And I have the numbers up here for you if you'd like them. But if you remember, the first step is list all the possible values. So stress values, you're going to list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are all the possible values that can be taken on. And then you're going to count. And you could either go through looking for zeros and go, I don't see any zeros. But there is one. I like to count just going 8. I cross it off and mark 1 for 8. I'm going to put little lines across here to make it easier to read. So I go, there's 1, 8, and then I know I don't miss anything. Here's a 7, 4, 10, 8, 6, next one's 8, 2 9s, 7, 3, 7, 6, did I get that 7? 1, 2, 3, yeah. 6, 5, 0, 9, 10, 2 7s, and if I make a mistake, feel free to point it out. 3s, 6, 7. I'll do that every once in a while just to keep you on your toes and watching. 2, 1, 6, and 7, 10, and 2 8s. All right. Now, if you just look at these counts, doesn't that kind of look like a histogram? If you had turned it this direction or a stem and leaf plot, you can see most of your scores are here around 7. So it's already summarizing the data a little bit, giving you some information. So now we're just going to summarize it in numbers instead of little tallies. You just go through and count the tally marks. 1, 1, 2, 3. Now, even if you didn't have these tally marks, some frequency tables just look like this, and that still gives you some information. You can go, oh, 7. I know most people, there were 7 people out of the class that scored 7. But if you were only looking at one of these and you didn't know how many people were in the class, it wouldn't be very useful. So now to get the frequency, all you are going to do is you're going to take the total number of scores, there are 30 of them, and you take each frequency or each count and divide by 30, the total number of observations. So the first one is 0.03 or multiply by 100, and we have 3%. These are the same, 1 divided by 30, 3%. And what is 2 divided by 30? You should be doing this along with me. It's 6%, obviously, since 1 2 times is 6 here, the 3 2 times. 3%, 6%. I'm guessing this is going to be 12%. 7 divided by 30 is 23%. So you see we have 23% that most of your people fell into this 7 category. Here, and you can see all I'm doing is 3, the number of counts, divided by 30, your total. To get your percent, you multiply that by 100, and 3 divided by 30 times 100 is 10%. Hopefully you followed those steps there. And there you go. Congratulations, you have created your first frequency table. Now you'll need this, go through, practice, do your homework questions, and you'll do great. If you need to, rewind it, watch it again, practice a couple times till you have this down pat. All right, now that we've created a frequency table, many times you will want to create a grouped frequency table, especially if you're dealing with a continuous variable like height that we talked about earlier. You wouldn't want to create a category for every single number, or even exam score. You wouldn't want to do 0, 1, 2, 3, 4, 5, 6, 7, 8, because that's going to require a whole lot of counts. So many times these possible values, instead of putting 1 through 10, we create groups like 0 to 1, 2 to 3, 4 to 5, 6 to 7, 8 to 9, and 10. 0, 1, 2, 3, 4, 5, 6, 7, 8. And so then you just count up. You would go through it and count 8 goes into this category, 7 goes into this category. So now you've grouped them where you can get some meaningful information, but it's not so much detail. I'm not going to run through this with you because it's exactly the same as we did before. Count them up, tally them up, count them up for the frequency, divide the total frequency by the total 30 to get your percentage here, and you should end up with something that looks like this. So why don't you go ahead and do this, pause the camera or pause the video and go through, work out this problem, see if your answers match up. If it does, you're great. If not, go back and try to figure out what you did wrong. Okay. After you have a frequency table, you can move on and build a histogram, just like the graph we looked at before. Now, to build a histogram, you need to first make a frequency table, Second, you need to list the values on an x-axis. So this is your x-axis down here. And this x-axis represents the values of whatever variable you are studying. So here we would put stress scores. And it always starts off with the lower numbers here and the higher numbers to the right. Lower this direction, higher this direction. Okay. So you might put stress score 0 here and the top stress score 10 here. That's your second step. Oh, let me move that up. Here we go. So you want an x-axis, your variable, and your values, 0 to 10. We'll put 5 here in the middle. Okay. Your second, after you've done that, your third step is to create a y-axis. This is your y-axis, and that y-axis just represents frequencies. So once you have a frequency table, it's very easy to change it into a histogram. There are scores, and if you were creating a frequency table with every one of these scores, then your histogram would have a bin for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you could group them and have 0 to 1, like we did before, 2 to 3, 5 to 6, 7, 8, and 9 to 10. So let's go ahead and try that. Let's see. Your 0 to 1, we had 2, so you would go 1, 2, 3, 4, 5, 6. This isn't to scale exactly, but when you have more space, you can make it to scale. But you would just count the frequency. So in our 0 to 1 group of students who rated that they were not stressed at all, there were 2 of them. So you just go up 1, 2, and here we go. You create a bin and you fill it in. Now, students who rated 2 to 3, so a little bit of stress, there were 3 of them. So we go up 1, 2, 3. It's just counting how many fell into that 2 to 3 category. And, oops, we're missing a 4 in there. Create a bin for them. The 4 to 5 category, we had the same, 3. So here we go, 4 to 5. 4 to 5 in here. And 6 to 7, we had 11 students in that group. So you're going to have to go up a little bit further, 7, 8, 9, 10, 11. So I'll just make mine go up right through here. And we'll go here, and this is your 6 to 7. And then 8 to 9, we had 8 students. We'll come down to 8. 10 to 11, we had 3 students. So my graph is a little messy, but you get the idea. You have the scores on the bottom, the frequency on the top, you create bins, and it gives you this nice looking little histogram. Hopefully yours looks a little nicer. And this tells you something about the data that you're working with. It says most students were in this 6 to 7 group. Okay, they scored moderate to moderately high stress. Very few students were in this low group. Okay, 0 to 1, very few students. So it tells you something about this group of students who's taking a statistics class. All right, if I were you, I'd pause the video now and do a few more. Practice making histograms. You're going to need to know how to make frequency tables and how to make histograms. I am going to move on and talk about, once you have a histogram, the distribution or the shape of the histogram. Now, this has a shape. This histogram has a shape. If we go back to the histogram we looked at earlier, remember this is a bar chart, this is a histogram. This histogram has a shape, and this shape is meaningful. Now, the shape is meaningful because it tells you very few scored low, very few scored high. Most students scored here in the middle. If you look at the bar chart, this also has a shape, but that shape, does it mean a whole lot? No, because we could have moved the brain regions around. We put hypothalamus first and amygdala second. Or if we were looking at hair color, you could move blonde and redhead, move them around and make it go down this direction or the other direction. So the shape, the flow, doesn't mean as much with the bar graph as it does with a histogram. So now we're going to talk about the shape or the distribution of histograms. Now, here are a couple of distributions and some terms we use to describe distributions in statistics. Now, this just looks like a mountain, but this mountain came from somewhere. Imagine that this is a histogram. So this actually had bins, and they just fit that mountain on top of those bins. Just like we made a histogram before, they just drew a line of best fit. Let me give you an example. So if I drew a line over this, it might look something like that. And so we're looking at this line instead of each individual bin. Now, this line that represents a histogram, this is what we call unimodal. Unimodal means that there's only one mode. And here, when we're talking about distributions, a mode is a center of data where most of the data is. Right here, you can see most of the data falls right here. Because the frequency is on this side. Remember, a histogram has the frequency on the y-axis. So this frequency is really high here in the middle. And as you get away from that middle, it tapers off, less frequency. There's only one spot with this big chunk of data where most of the students, or whatever variable this is, fall. And this is what we call a unimodal. Now, sometimes you get two different peaks of data. And there's a little one, but that you see, it's not very much, and there's not very many people fit there, even though it starts to peak back up. Here we have two places where there's really the majority of your data. The frequency is really high on those two. And this is what we would call bimodal. Sometimes you have two different centers of data. And a good example might be height. You might take the height of men and women, and on average, men tend to be a little higher. So you're going to have this high frequency of height up here, and then the average of women might peak down here, and you end up with this bimodal set of data, two different modes. When we get into chapter 2, we'll talk about mode, calculating a mode that's a little different than this type of mode. This just means where there's a big chunk or the most of your data. And sometimes the most of your data falls in one spot, unimodal. Sometimes it falls in two spots, that's bimodal. Sometimes you get 3 spots of data, and that is multimodal. Okay. This third example down here is approximately rectangular. Doesn't really look like there's one lump of data that is the most frequent. It's approximately rectangular even across it. That's also what we call uniform. Uniform data looks rectangular. Now, along with those unimodal, multimodal, bimodal, and uniform or rectangular types of descriptions for distributions or shapes of data put into histograms, we also have what we call symmetry and skew. Now, the distribution is symmetrical if it looks the same on both sides. So the data we were looking at, let's see, here's a good example of symmetry. Both sides are the same. We'll come back to this in a second. Now, these two graphs, as you can see, are not symmetrical. So if we just look at this first graph, the distribution is not the same on this side as it is on this side. It doesn't look like a mirror image that has been folded in half. It has a little bit more data that tapers off to this side. This is what we call right skewed or positively skewed. Right skewed means that most of your data is on the left, but there are some outliers. Outliers are kind of extreme scores that don't fall with the rest of the data that taper off towards the right. Also called positively skewed because those few scores that are pulled way up here, our outliers, are up towards the higher end, or the positive, versus 0 or negative if you're going down to the other part of your x-axis. Positive and right skewed. The opposite of that is negative or left skewed. Most of your data is on the right, and then you have a few scores that taper off to the left, or the negative side. So these are important things to understand. You need to be able to identify whether your data is symmetrical, whether it's left skewed or right skewed, before you can determine the appropriate statistical tests to use. And sometimes you get data that kind of gets right skewed because it's stuck. Most of the scores can't go below a certain number. For example, if you're looking at age, you can't get an age that's below 0. You can't have a negative number for age, so it's going to stop here. Most of your data will be around some center, and then you might have a few people that live until they're a really long time, but those are going to be outliers. Most people live a normal range of life, but you can't get any lower, so you're going to have a right-skewed variable. Okay? That's what we call a basement effect. A basement effect is when you can't go below a certain point, and a ceiling effect is when you can't get above a certain point. For example, suppose you took an intelligence test, and at the end of this intelligence test, the max you could get was 230. Okay? Since that's the max, you can't get above that. This may have been symmetrical had the test given you more options over here on this end. So many times a ceiling effect, or a block that you can't go past, creates a left or negatively skewed variable. Now, my favorite distribution, this is what we call a normal distribution. Now, a normal distribution is a bell shape, this bell-shaped curve. And if you've ever, been introduced to statistics, you probably are familiar with the shape. From now on, you will not call it a bell shape. You will call it normal. If someone on the street asks you if you're normal, you just say, I don't know, let me see, and see if you have these properties of this bell-shaped curve. The properties of a normal distribution are that it is symmetrical. So as you can see, one side approximately symmetrical. If I fold it in half, it looks like the other side. It's a mirror image. You can split it right here in the middle and it looks the same on both sides. It has to be symmetrical. Another property of a normal curve is that most of the data falls in the center. It is unimodal. Most of the data falls in the center and it tapers off as you go towards both ends. Now, there are a lot of variables that follow this normal distribution. That's probably because in life there are a lot of averages. Most people fall around the averages. If you think of height, most people are average height. As you get taller, remember this is a frequency, as you get taller, fewer and fewer people are going to be in that category. As you get shorter, fewer and fewer, little midgets are going to be in these categories, but most people are around this average. Same thing typically happens for many, many, many variables, and this is a very important distribution to understand. We'll learn more about it. There are certain properties of the normal curve that we will be using to calculate our statistics. It's fundamental to understand the normal curve to be able to understand how many of our inferential statistics, which is going to take up a good portion of this class, are developed and how those statistics work. Now, let's move on to some misleading graphs. You have probably heard somewhere that statistics lie. I've heard people say, oh, I don't like stats because statisticians lie. They can turn in things any direction they want and make you believe whatever they want you to believe. Well, it can be true, but it's a lot easier to lie with words than it is with numbers. And the benefit you have of taking this class is that once you understand the statistics and the numbers yourself, it can't lie to you. You understand the numbers, you can't be misled. You go, and you catch those things yourself. So here are a couple things to look for when you look at graphs, when you watch things on TV. And a couple of things to look for are equal intervals on graphs. Sometimes you get one graph and they will use a certain number of intervals, and then you get another and they shrink it and it gives you a total different appearance for the graphs, and they can change those intervals to make you believe different things. So you want, when you're comparing one graph to another, you want to make sure that those intervals on both graphs are the same. So I'm talking about the y-axis. You want the same numbers on your y-axis when comparing graphs. Another thing to be careful for is truncated graphs. I have an example of truncated graphs. This is where you don't start the bottom of your y-axis on 0. And there are some reasons to truncate graphs to make things look differently, but you need to be aware of that when you are looking at graphs. And then sometimes people exaggerate proportions on the graphs. Let me give you an example of this. Now, and this may be too small for you to see what is labeled, but this first graph, here I'm going to cover up the second graph first. This first graph tells you different brands of trucks. Okay? Now this is a bar graph because you're using a categorical variable down here. Different brands of trucks. It has our brand, brand X, Y, and Z, And then on the y-axis, it gives you the percent still functioning after 10 years. So pretend you were in the market to buy a truck, and you're sitting and the car salesman is showing you this graph, and they say, here's our brand of truck. Look at what percentage we have surviving after 10 years. This is great compared to all these other brands of trucks. You go, wow, great, I want to buy this truck. And they go, and our truck only costs $5,000 more than these other brands, but it's worth it. It's worth it because of this difference here. Now, note, where does this graph start? It starts at 95%. So if you were actually looking at the numbers, every single one of these brands has over 95%, probably over 95% surviving. So is it worth the $5,000 to have 95% chance your truck will survive after 10 years versus 98%? Not that big of a difference if you're actually looking at the numbers, but it looks like a big difference if you just look at the bars in the picture. So here's another graph. This is the exact same set of data. If the car salesman had shown you this picture, this graph, and said, here is our brand, and here are the other brands, and here's the percent still surviving and functioning after 10 years, would you go, all right, here's the extra $5,000, your brand's the best, let's go for it? No. It looks like the difference, it looks like there really isn't a difference. It looks like the difference is so small that it's not kind of minuscule, not even worth paying attention to. So these two graphs came from the exact same data sets. That's why it's important for you to understand statistics, look for the details of these statistics, be able to look at the numbers and interpret the graphs yourself. If the graph is truncated, starting at 95%, they should really mark that on there, put a little note so that the reader is aware of this. But even being aware of it, sometimes pictures are stronger than words. So the numbers are going to give you the truth. You look at the numbers and make your own decision. Try not to be swayed by these influential pictures and graphs. All right, so just to recap, we went through different, making a frequency table, making a histogram. We went through different types of graphs that can be used, pie charts, bar graphs, histograms, stem and leaf display, some things to watch out for when you're looking at graphs yourself. So you should be on your way, and I will see you next time.